In this video, we're going to be covering the sample distribution of the mean and the central limit theorem. First, we'll suppose that we have a population of data, and for an example, so we can see what's going on here, let's suppose we have the population of size 5, so our capital N is 5, our population size is 5, and let's suppose the specific values are 4, 6, 6, 7, and 7. Well, what does the population mean? The population mean is, right, we use mu for this. Mu is equal to, and then we have 4 plus 6 plus 6 plus 7 plus 7, all divided by 5, which is 10 plus 6 is 16, plus 14 more is 30 over 5, or 6. So that's our population mean. And then, let's find the sample mean of size 2 without replacement. So what does this mean? This means we take all sample sizes of size 2 and we find the mean of those. Well, how do we find that? We have 10 different samples of size 2 that can be made from 5 values without replacement. And how do we know that? Well, that's equivalent to finding 5 choose 2, right? We have 5 values, and we want to choose 2 of those values, right? This is 5 choose 2, which is 5 factorial over 2 factorial times 5 minus 2 factorial, which is 3 factorial. 5 factorial over 3 factorial leaves us with 5 times 4, and 2 factorial is just 2, so this is 5 times 2, or 10. So that's how we get the 10 different samples of size 2. What are those 10 different samples of size 2? Well, recall our population data here is 4, 6, 6, 7, and 7. So what are the possible samples of size 2? Let's write those down. So we have sample. And we're going to write our mean over here because that's what we're going to calculate here in a few minutes. But what if our sample is 4 and 6? We also have another 4 and 6 possible. 4 and 7, 4 and 7. And those are all of the samples of size 2 with a 4 in it. And then let's write down a few more. Let's see, we have a 6 and a 6. We have a 6 and a 7. We have a second 6 and a 7. And then we have 6 and a 7. 6 and a 7. 1, 2, 3, 4, 5, 6, 7, 8, 9. And our very last sample size of size 2, or sample of size 2, is 7 and 7, which is the last 2. Okay? And from those 5 data points, those are all samples of size 2. Well, what are the means of each of these samples? Well, we have a 5 here. The mean of 4 and 6 is a 5. The average of 4 and 7 is 5.5. 4 and 7 is 5.5. 6 and 6 is a 6. 6 and 7 is 6.5. We've got that happening several times. And then we have a mean of 7 there at the end. Well, what do we have? We have 10 sample means. And notice the average of these means is of these sample means is, well, let's go ahead and find out what that is. 5 plus 5 plus 5.5 twice plus 6 plus 6.5 4 times plus 7. And this is all divided by 10 because there's 10 things we are adding up here. Well, this is equal to, this top part sums to be 60. So that is 6. What does this suggest? Well, if we break up our population into samples of a certain size, and in this case, we chose our samples without replacement, and we find the mean of each of those samples, and then we average all of those means, we get the population mean that we started with. And it turns out that's always true. And in fact, even if we chose our samples with replacement, that would still be true. If we find our sample means and we take the average of those, we will always get back to the population mean. Now, why might that be important? Well, let's look at the last bit here of this video, which is discussing the central limit theorem. So it turns out, as the sample size, so the number of values in each sample, gets large enough, and what do we mean by that? Generally, that means if we have a sample size of 30 or more, then the sampling distribution of the mean. So what is that? What is the sampling distribution of the mean? That is all of these values. So this is our sampling distribution here, is those 10 values. This sampling distribution is approximately normally distributed. This is true regardless of the shape of the underlying data or the shape of the distribution of the underlying data. So our underlying data, our population, could be right skewed, it could be left skewed, it may not be normally distributed, but if we look at the distribution of the sampling mean, that data will be approximately normally distributed if our sample size is large enough, no matter what the underlying data was. And that's really nice to be able to use because we know what a normal distribution looks like, and we know how to work with that. We've been able to do that in the several previous sections. So if we can look at our data and turn it into something that is normally distributed, then we have a powerful tool to make our work a lot easier and to be able to find a lot of information a lot simpler. That's it for this video. Stay tuned for the next video when we're going to do a couple of examples on this type of information.